Okay, it's loading now. Okay, all right. Good evening, everyone, and welcome to our first Michaelmas talk for the Oxford University Space and Astronomy Society. I'm Hannah, I'm your society president, and I'm very, very delighted and excited to be able to put on a range of talks for us this Michaelmas. Some of you will be familiar with the usual in-person setup over at the Department of Physics, followed by refreshments thereafter. Sadly, circumstances mean that we're having to move things online, but not a problem. We're still able to bring in some fantastic speakers to speak to us about their research. And I'm very, very delighted and very, very honored to have Professor Niranjan Thatte here today. He will be speaking to us about his research on the Extremely Large Telescope. So a little bit about our very special speaker today. So Professor Niranjan Thatte is a professor of astrophysics at the Oxford Department of Physics. His research focus is in astrophysics instrumentation. He is the principal investigator of HARMONY, which is the first light instrument for the European Extremely Large Telescope, which he'll tell us about more very shortly. And prior to becoming a faculty member at Oxford, Professor Thatte received his doctorate at Berkeley and was a staff scientist at the Max Planck Institute for Extraterrestrial Physics. So lots of exciting research and experience to share with us today. So without further ado, over to you, Professor Thatte.
Thank you very much for the introduction. Pleasure to be here virtually. Would have been nicer to have been there physically. But anyway, I'll start sharing my screen and hopefully you can all see a presentation shortly. So can you see the title slide now?
Yeah.
Okay. All right. So I'll get started. Right. So I'm going to tell you something about the Extremely Large Telescope, and I'll start by explaining
Seems to have lost you for a minute.
move my slides forward or back.
Okay,
yeah,
yeah,
here we
back.
go. Oh dear. Okay. Can you still hear me? Because it said my internet connection is unstable. Hopefully it's...
Yeah, we can hear you now, yeah.
All right, okay. Right, so this is a rogues gallery of some of the large telescopes that are operating around the world today. And you can see that all the big telescopes are mirror telescopes, and that's for a very good reason, because we have to support the structure against gravity as we point it to different directions in the sky. And if it is a lens, then we can only hold it around its edge, which means that it sags under its own weight due to gravity. And that makes life really difficult because it causes all sorts of aberrations in the optics. So mirrors are much better because the polished side pointing towards the sky. And then we have the back side, which we can use to support the mirror structure adequately. So almost all professional telescopes, unlike amateur ones, are mirror telescopes, and astronomers have very nice, very imaginative names for them. So the current one that is operating in Chile is called the Very Large Telescope, and the project I'm working on right now is called the Extremely Large Telescope. So you can see we are very imaginative in our nomenclature. In fact, there was a concept for a 100-meter telescope, which was called OWL, which stood for overwhelmingly large, right? And that unfortunately hasn't gotten built because of budget issues. So the acronym OWL now stands for originally was larger. Anyway, so why do we need very big telescopes? There are two main reasons, and I'll try and explain both of them in a bit more detail. So the first one is, of course, big telescopes have a lot more collecting area, or light gathering power, which means that we can see really faint objects because we can collect the light over a much larger area. Now, fainter usually means more distant, but not always. There are some objects that are relatively close by, like planets around other stars, which are still very, very faint. So the ELT will allow us to see exoplanets, amongst other things. But more typically, it does mean that the fainter the object, the further away from you it is, because of inverse square law, reduction in the amount of light that we collect. It also means that if the object is further away, that the light has taken a much longer time to reach us, which means that we see the object as it was a long, long time ago, right? And so this is why big telescopes are powerful, because they are time machines, because they let us look back into the history of the universe. So we can go all the way back to when the universe became transparent, and so we can see the light. So the photons have been propagating from these early galaxies for billions of years. Today we are at something like 13.8 billion years, and we can look back to less than a billion years since the birth of the universe. So that really gives us a look back time, which allows us to look at the evolution of galaxies and how they formed in the first place as well. So how big is the ELT going to be? So this is a chart which shows, just has axes, which is the altitude and the time, just to separate the different telescopes that we have built to date. And the size of the circle is proportional to the diameter of the telescope. The biggest ones to date are the 10-meter Keck telescopes on the island of Hawaii. And the 5-meter Hale, which is on Palomar Mountain, is really quite a impressive machine. It is now well over 50 years old and is still doing wonderful science. The ELT is going to dwarf all of them with a diameter of the primary mirror of 39 meters. That's almost half the size of a football field. And it's very hard to imagine how big this structure is really going to be. I'll show you some CAD models and some pictures from the ground later. But the area of the ELT is almost equal to the area of all the telescopes we have built until now put together. So it's going to become going to mean a big leap in our light collecting ability, and therefore in how faint and how distant the objects are that we can see. So let's try and quantify that. How much bigger, how much fainter can we go with a big telescope? So if you look at the pupil of the human eye, dilated at nighttime, it's about 4 millimeters in size, give or take a little bit, versus the 40-meter diameter of the ELT aperture, nearly 40-meter diameter. So that's a factor of 10,000, and in area that's about 10 to the 8 or 100 million. Right, and so that's where the title of the talk comes from. We have essentially the light gathering power of 100 million human eyes put together. Now, as you know, astronomers measure stellar brightness in magnitudes, with 1 being the brightest that one can see with the naked eye, and 6 being roughly the faintest. Depends on the night and your eyesight. But and then this sort of rough scale was put on a proper mathematical footing by a long time ago, by saying that 5 magnitudes is exactly a factor of 100. So it's a logarithmic scale. And so 100 million means about 20 magnitudes. So if we can see a 6th magnitude star with the naked eye, then the ELT should be able to see a 26th magnitude star or galaxy. Right, but we can gain even more because we can expose for longer, because the human eye, because it is made to sense motion, because it's not really interesting from us from biological evolution to be able to just look at stationary things. So we have an exposure time or an integration time of something like 1/10 of a second. It's a bit shorter than that typically in daylight, which is why television or movies need 50 frames a second to give you that feeling of continuous motion. But at nighttime, it can be a bit better, so something around 1/10 of a second. With the ELT, we could easily expose our cameras, our detectors that are collecting light for something like 1,000 seconds. So that gives us another factor of 10,000. So we should have been able to go down to something like 36th magnitude, but actually we can't because we are limited by the sky background. So when the background becomes bright, then you start being dominated by the photon noise or the shot noise from the night sky itself. And so we gain a little bit less than we would have anticipated, but nonetheless, it's going to be a huge revolution in amount of light we can gather, and therefore how faint an object we can see. Okay, so that's one reason why we build big telescopes. The other reason is that bigger telescopes in principle yield sharper pictures, okay? And this is a result that comes from the wave nature of light and the angular resolution, so the ability to tell apart 2 points as pinpoints of light on the sky that are separated in angle by a teeny tiny amount is proportional just to the wavelength of light at which you're making the observation and the diameter of the telescope. So this is diffraction theory, but I'll try and explain in a very simplistic way, a poor man's explanation for where this limit comes about from. Okay, so consider our telescope, right? So that's the parabolic mirror here at the bottom. Let's see if I can get a laser pointer. Now you can see, so that I've got my parabolic mirror here at the bottom and such that rays coming from infinity all parallel to each other would come to a focus at the focus of my telescope, which is where I've drawn this star image. So for a point source, we would expect what we call a plane wave front, so that, you know, essentially the crests of the waves would all line up along this line. So let's say if the telescope was in space, then this would certainly be the case. And then you would get this plane wave front coming in. Now the parabolic primary mirror has the property that the distance from sort of this horizontal line here up to the mirror and back to the focal plane is the same for all the different ray paths that you can think of, which is why the image is produced here at the focal plane, right? But light is not really rays, it's really a wave. And so to think about sort of what the diffraction limit image would be like, which is something like this, it's called an airy pattern. And that's what you would see if you pointed an ideal telescope at a star or a point source in the sky. So where does this come about from? So to figure this out, let's think of just two pieces of our telescope. So I've just drawn the outer edge on the left and the outer edge on the right, but the argument, of course, works for any pair, right? And you can see that now the path length from the black line via these mirrors is the same to this point, which is where the stellar image lies. So that's the peak of the image in the middle here. But because the light is the wave, we must really think about all the different paths that are possible from the light hitting the mirror to the focal plane. So these red arrows are not following the law of reflection, because I'm now giving you a poor man's explanation of diffraction where the light is to be treated as a wave. So you should think about the light as sort of filling the focal plane everywhere with light reflected off of this mirror segment rather than just the specular reflection that you normally consider in geometric optics. So what about these two red rays? So if we line up the two red rays next to each other, you'll see that actually the path length is not the same, which is true of the blue rays. And so therefore these two rays have a different property. And now if you invoke the wave nature of light, you'll see that if the difference in the path length of the two red rays becomes equal to half a wavelength of the light, then instead of having constructive interference to produce this bright peak in the middle, we will now have destructive interference between these two red rays, and we will create what's called the null of the airy pattern, where essentially there will be no light at all. And in fact, if you do the analysis with the full aperture of the mirror, you will get not just one point, but rather this ring due to the circular symmetry. And so that's where, that's sort of a rough explanation of where this comes about from. Now, of course, the further apart you space these two pieces of the telescope, you can see that the path length difference is going to be larger. And therefore, the distance you have to go off axis before you get to the first null is going to be smaller. So in other words, the bigger the telescope, the sharper the picture, because the distance between the peak and the first null is going to be smaller. So if there was now a star located at the location of this null, a second star, which is drawn in green with a tilted wavefront, because now you're pointing at a different point in the sky, you would be able to see this star as a separate star. And indeed, we can invoke a criteria that was first defined by Lord Rayleigh, which is called the Rayleigh criterion, which says that if the peak of one star lines up with the null of its neighbor, then we call the two stars as just about resolved. And that then gives us, in numerical terms, the diffraction limit of a large telescope, which was this formula I showed you earlier, which is 1.22 times lambda over d. So if you plug in the numbers, if you go to a diameter of 8 meters, which are the VLT telescopes in Chile at the moment, and half a micron, which is visible wavelength light, you would get something which is 15 milli-arc seconds, right? So an arc second is 1 part in 200,000 roughly, and this is 15 thousandths of that. So really a very tiny angle on the sky. Do we achieve that? No, we don't, unfortunately, nothing like it, right? Here's what you would see if you took fast images with a TV camera at the focus of a large telescope. You would not see a nice stellar image. Instead, you would see this sort of patchwork of what we call speckles that dance around, and the whole blob moves around. And the thing that is responsible for all this mess is our atmosphere. Okay, this is the same reason why stars twinkle. And so to illustrate what is happening here, I've used the analogy from a pond. So if you have a really quiet day and you have a still surface of a pond and you drop a stone in the middle, then you get nice circular waves propagating outward, and this would be like the waves of light from a very distant star. On a windy day, though, those nice circular waves start to break up, and you get a lot of distortion in the waves. And the same thing happens to light from distant stars. It travels in nice spherical or plane waves because the stars are so far away. We're seeing only a tiny, tiny part of the circle. So for us, it's like a straight line. Until it hits the atmosphere. And then in the atmosphere, unfortunately, because the air has refractive index variations that are caused by density and, well, primarily by temperature variations, which cause density variations, and then refractive index variations, the time taken for the light to propagate through different paths in the atmosphere is different, and that causes this wave to get deformed. Okay, so it starts to look like this, and then our picture goes to pot, and instead of seeing the lovely airy pattern that I tried to explain to you earlier, we see that blur consisting of speckles. And this has made astronomers' life difficult for years and years, well, centuries really, until we came up with a scheme to figure out how we could combat this. So let's go back to our toy telescope and think about what the atmosphere is really doing to it. So now, instead of having the rays coming down as a nice plane wavefront, which is shown by the horizontal line, we now have two pieces of atmosphere, two different pieces in front of the left edge and the right edge of the telescope. And I've tried to show you that they have slightly different densities and therefore slightly different refractive indices. And so this ray on the left is delayed by a little less than the ray on the right. And this is going to cause our image of the star to get blurred, because now that constructive interference that we had at the focal plane from all these different rays that I tried to explain to you earlier about is no longer valid, because the different rays have different path length delays associated with them. right? So instead of a nice plain wavefront, we get this corrugated wavefront coming in, and our picture is no longer nice. So ground-based telescopes rarely ever achieve the diffraction limit because we are limited by turbulence from the Earth's atmosphere. But astronomers have found a way around this. This is called adaptive optics. And this is how it works, all right? So here's a nice movie made by the people at the Gemini telescope, and you see the light bouncing off the primary and then off the secondary mirror of the telescope. It then goes through a hole in the primary mirror to what's called the Cassegrain focus, which is normally where the instruments would be located. And here is one of the instruments, which is an adaptive optics corrector. So what does it do? So let's look inside. And so there's our science camera on which we are going to take images. There's the light from the telescope. It's coming to a focus here. We then have a collimating lens, and it goes onto a mirror and then onto what's called a dichroic beam splitter, so that the red light is being sent to our science camera to take images of the stars. And there's that familiar image I showed you earlier, made up of speckles. But the blue light is now being sent to a wavefront sensor. And this wavefront sensor is in real time analyzing the shape of this wavefront. So you can see all these twisted wavefronts coming in. If we now close the loop and send control signals from the wavefront sensor back to what we call a deformable mirror, right? Now, a deformable mirror is a very clever piece of machinery whose shape can be changed 1,000 times a second by moving actuators on its back. Then the wavefronts can be changed into being perfectly flat, and the images on our science camera have turned into perfect airy patterns with nice rings. Okay, I'll explain a little more in detail what is going on, but here's what you see. So two things happen in this demonstration. Now, first is that you still have speckles, but the whole blob has stopped moving around, which we call the tip and tilt correction or image motion correction. And then we turn on the higher order correction, and you can see it's not quite perfect, but it's nearly perfect. And you start to see the airy pattern with that nice dark ring and a few other dark rings and subsequent bright rings as well. So that's a demonstration of adaptive optics and how it works. Now, those of you listening carefully would have said, wait a minute, but that's not very helpful, because you already knew the answer. You knew that the answer was going to be a plane wavefront because you were looking at a point source, and you've turned your deformable component, your deformable mirror, so that you always get that answer that you already knew. So what good is it doing? The idea is that if you correct for the aberrations for this reference star, then that same correction is applicable also for a science object, a galaxy, say, drawn in this picture, which is located close to the reference star. So ideally speaking, you want to correct the turbulence created by this blue cylinder of air from the atmosphere above your telescope. Looking at the galaxy, what you've actually got is the correction measured by your wavefront sensor and then sent back to your deformable mirror for a reference star which is close by. And you can see from the way I've drawn this picture that as long as there is substantial overlap between the blue cylinder and the tilted gray or brown cylinder, then our scheme would mostly work, right? Obviously, there is correction that we are applying for this bit here, which is not useful to us because it only belongs to the reference star for which we know the answer already. And conversely, there is a blue bit here for which we are not measuring anything, so we can't apply a correction. So it's not really perfect, but it's close in, it's good enough as long as the reference star and the object are close to each other. So adaptive optics works extremely well, and we've used it for several decades now, but with the limitation that we need to have a bright star close to the object that we want to study. Now, why does it need to be bright? It needs to be bright because we are only integrating or exposing with our wavefront sensor for 1,000th of a second, and we need to go that fast because that's the time scale on which the atmosphere evolves. Now, this is mostly due to essentially winds at 10 or 15 kilometer altitude, and you can figure out how long it takes the wind to move at typical wind velocities, and you find that you have to correct in closed loop at something like a few hundred hertz, for which you need to sample at something like 1,000 hertz. Not only that, you need to sample across every little bit of the telescope where over which the atmosphere you can assume is constant. So the size of that is typically about 10 or 15 centimeters. So even if you have an enormous telescope, and that just means you have many more correcting elements, but it doesn't really mean you can gather more light from your reference star. So to some extent, independent of the size of the telescope we are building, the reference star has to have the same brightness. Unfortunately, there are not enough bright stars in the sky. So this wonderful technique of adaptive optics works, but it only works in the close vicinity of bright stars, and that's not enough for us. So here's the technique in a nutshell, and I'll explain to you in a second how we can circumvent that last limitation I told you about. But here again are the different components. So the key here is the deformable mirror, as I said. So this is a thin glass face sheet, which is only about 1 millimeter or 2 millimeters thick. And typically glued on the back of it are thousands of piezo actuators or magnets, and we activate these magnets with a voice coil like in a loudspeaker in real time at 1,000 times a second. And then the shape of this mirror changes in real time. So we actually push and pull on this glass face sheet so that it deforms. And if we put the exact opposite of the atmospheric deformation onto this rubber mirror, then what we will get out will be nice plain flat wavefronts or flat pancakes. Okay, so if we can do this, what is the gain, right? The gain is enormous. So here's an example of what you might see. So this is what we call a seeing limited picture. So this is limited by atmospheric turbulence. The size of this picture is only about 1 second of arc on the sky. So remember that the full moon or the sun is about 30 arc minutes. So that's about 1,800 of these arc seconds across. So this is really a tiny portion of the sky we are looking at here. And you can barely see any detail because the seeing limit is roughly about typically about an arc second. Right now, if you were to go into space and look with the Hubble Space Telescope, that has no atmosphere, so it doesn't suffer from this. So you get much sharper pictures, of course. But the Hubble is not a very big mirror. It's only 2.4 meters across. So the diffraction limit, that 1.22 lambda over d that I showed you earlier, comes into effect. And this is the limit of resolution that you can get with the Hubble. Now, we can't put bigger telescopes easily into space because it costs a lot to put telescopes into space. We can build bigger telescopes on the ground. So with the current generation of 8-meter class telescopes with adaptive optics, we can actually do better, right, than we can from the space telescope, simply because if we can achieve the diffraction limit and combat the turbulence in the atmosphere, then we can reach much higher resolution than the seeing limit, right? So maybe go back, sorry, another way, right? We can go from this picture to this picture with current generation telescopes. And then if we went to the ELT, this is the level of detail we would see. So you can see that the use of adaptive optics has led to a huge revolution in terms of the level of detail and the resolution we can get in the sky. Okay, so back to my limitation, what can we do that, we don't have enough bright stars in the sky? Well, let's make our own, right? This is what astronomers have been doing for the last 10 or so years. And what we do is, because we don't have a reference star available where we need it, we shine a laser. We shine a laser into the upper atmosphere and we create our own artificial star. We create it right on top of the galaxy so that we can exactly measure the turbulence of the Earth's atmosphere. So if you see images of telescopes with lasers shooting out the sides of them, that's why, right? We use these lasers as reference to generate reference sources with which we can run adaptive optics. So the laser star works. It obviously is not at infinity, but it's high in the atmosphere. And so actually what it senses is not quite the blue cylinder that we were interested in earlier, but rather this orange cone. And so there's still a limitation to how well you can correct with a laser star, but it's plenty good enough. And if you wanted to really fill in this blue hole on the left here, you would just need an additional second laser star or a third or a constellation of them. So that's what we will use for the ELT. We will use an asterism of 6 laser stars to do our bidding. So how does that work? So here's another movie that shows you how laser stars operate. So this is again courtesy Gemini telescopes. And what you can see here is the solid state sodium laser. So sodium, because there is sodium in the upper ionosphere of the Earth's atmosphere at an altitude of about 100 kilometers. And so if we shine a laser tuned to the line of sodium, it doesn't impact the measurements we are making with our telescopes cameras, because it's in a very narrow band pass and we can reject that light very comfortably in our spectrographs or spectrometers, but then it does. So there's the beacon, the laser beacon shining off of the secondary, the back of the secondary of the Gemini telescopes. In the case of the ELT, it will be what we call side launched. So we are now zooming up and we see the island of Hawaii where the Gemini telescopes are located on Mauna Kea. And now we are up into the upper atmosphere. And you can see the laser beam that we shown from the back of our secondary. And when the altitude gets to about 90 kilometers in the sodium layer, we now excite the sodium layer in this D2 orange transition, the same line that you see in street lamps. And that orange transition then allows us to create an artificial beacon, an artificial point source reference that we can use as our adaptive optics reference. And with that, we can correct. Right. So that's the idea behind the ELT. So this is the CAD illustration of the structure. That's a lorry. Those are cars. So you can see the whole structure is basically about the size of a football stadium. The primary mirror itself, as I said, is about half the size of a football field and has a huge dome associated with it. The whole structure is going to be built on a mountaintop in northern Chile in the Atacama Desert. And there is an observatory not too far from where the ELT is going to be built. So the ELT is back here on Cerro Amazones at an altitude of about 3,000 meters. And the current observatory that the European Southern Observatory runs is the Very Large Telescope. And that's the structures here. There are 4 telescopes, each with 8-meter primary mirrors on Cerro Paranal. And on a subsidiary peak, there's a small 4-meter telescope that is called Vista, that is doing all sky surveys more like, and you can see the residencia and the base camp structure here, and the road joining Paranal and Amazonas is indicated there as well. So that's where the ELT is going to be located. And let's look at what this telescope is going to look like. So this is actual picture from a webcam. You can go to the ESO webpage and you can see there are live pictures being streamed from Chile all the time. And that's the status that was earlier this year. And this is a slightly more recent one. Unfortunately, because of coronavirus, construction has stopped at the moment. So you don't see anybody on the mountaintop. But as you can see, the structure for the ring and the dome and the tracks for the azimuth of the dome are already laid out. It's a few years since construction has begun on the mountaintop. They first had to flatten the mountaintop, and now they're starting to put in the concrete structures. The rest of the telescope, including the mirrors, etc., is currently being built in Europe and will be transported to Chile. I'll show you more about that in a second. But first, a bit about the optical design of the telescope itself. So this is the ELT. The primary mirror is made up of 798 hexagonal segments. That's because we can't make a single monolithic 39-meter mirror. The biggest we can make are about 8 meters. Believe it or not, that is limited by the size of motorways or highways in the USA. So we make it instead out of segments, hexagonal segments, which we close pack to essentially form a complete surface on which we can put the wonderful reflective coating that we need in order to make it a hyperbolic mirror. That then would focus the light somewhere up here where my laser pointer is, but instead what we do is we pack it into a shorter length tube So there's a secondary mirror. It's not floating in space. There is a real structure around it. This is just shown for clarity. And normally that there would be just the primary and the secondary mirror, and they would relay the focus to the side to one of these platforms here, which is called the Nasmyth focus of a telescope. And that's where we would locate the instrument. The advantage of the Nasmyth platform is that it only rotates with the telescope in azimuth, but it doesn't change altitude. And therefore you can have much bigger instruments because they don't have to be articulated together with the telescope itself. In the case of the ELT, though, it's the first or one of the first adaptive telescopes. And so what we have done is we have planted a fourth mirror in here. So the light from the primary comes to an intermediate focus, then goes to a concave M3 mirror, which turns it back into a collimated beam, which then goes to this M4 mirror, which is in the shape of a ring or a donut. This is the adaptive mirror with the 2mm glass face sheet and 5,500 actuators behind it, whose shape we are going to control 1,000 times a second every night for 30 years, or whatever the lifetime of the observatory will be. And then that just reflects off a flat mirror that does the image motion correction, the slow tip and tilt, and that is then the beam is sent to the science instruments where it will be harnessed by spectrometers or cameras in order to do the analysis of the light that the telescope has gathered. So here's a little video showing the light path that may make it easier to understand. So there you see it's reflected off of M2 and then M3, M4 and M5, and then goes to the instruments located on the Nasmyth platform. So I'm responsible for the consortium that is building one of these instruments, which is called Harmony, which is a spectrometer that will analyze in many different colors the light collected by this 39-meter telescope. Okay, so everything about it is superlative. It's an enormous thing. The main structure is 2,500 tons of steel moving several hundred tons of optomechanics and electronics. The dome itself is another 5,000 tons of steel that has to move on its azimuth track. So ideally, when we are observing at night, we don't really want a dome at all. We want the telescope to be open to the atmosphere because we want to have as good air exchange between the telescope structure and the outside as possible, because of course any changes in temperature lead to turbulence, and turbulence leads to artifacts or aberrations in the image that the telescope will produce, which we'll have to cancel with our adaptive optics. So the less of it, the better. But however, on those few nights when the weather is inclement in the northern Andes, we do need a dome to protect the telescope against the elements. And also, more importantly, in the day, we need to protect it against the sunlight. Otherwise, it would get very hot and that wouldn't be so nice. These platforms where we're going to put the instruments are themselves quite large. They are about the size of a tennis court, and you'll see some CAD models later of what they look like. So it's going to be huge platforms. The tip of this structure is, as you can see in this picture, 65 meters high. So we've got, a secondary mirror, which is about 4-meter diameter, hanging 65 meters up in the air. So that's just another view of the structure and the optical path, which I already showed you. A little bit more about the primary then. So the primary is made up of these 800 hexagonal segments, and a lot of work has gone into making the segments really be part of a single mirror surface, right? That's quite difficult because you need to do that to a fraction of the wavelength of light. So the wavelength of light is in the visible is about 0.5 micron. So you want to do this to something like a tenth or even better than that of that number, right? So we are talking about 0.05 microns of offset allowed between adjacent segments. Not only that, as this whole telescope points to different parts of the sky, the gravity warps the shape of each of these segments. So they are about 1.5 meters. They're still quite massive, and they warp under their own weight. And so there is this big structure, mechanical structure behind them with hexapods and load-bearing trusses and structures to keep the segment shape. And then, of course, we have to make sure that this segment lines up on all its 6 edges with all its neighbors. So there are edge sensors continuously working in real time that ensure that all of these 800 segments make up the surface of a single mirror. They also need to be coated with something reflective, and that coating wears away, unfortunately, because it's exposed to the elements every night that the telescope observes. So we have to be able to recoat the primary mirror, as all other mirrors as well, of the telescope. And this is a really mammoth task. It's a bit like the fourth bridge, because you start at one end. By the time you have re-silvered or re-illuminized the segments all the way across the telescope to the other end, it's time to start back on the left edge again, because the whole process will take us something like a year or two. So if you want to keep the coating to have an average age of no worse than a couple of years, then you continuously need to have every day an operation to remove a couple of segments, take them off to the coating lab, recoat them, and replace them with a spare set. 1/6 of this is so we have actually a 7th set of 133 spare segments, which we will use to replace the ones that we will take out during the day. So here's the details of that. You can see some of the hexapod structures, some test segments that are being made already. And so I talked already about these 6 families of 133, so that we have an extra spare set. And here you can see a movie of one of these segments in one of the test setups at ESO being raised above the rest, so that then the overhead crane can come and pick it up and take it off to the coating lab while a new segment can be put back in place. So in a lot of ways, a big modern telescope is like a Formula One car, in the sense, you have to work at it every day during the day for almost 10 or 12 hours before it can be ready to provide you service for the night. And then the next day you have to do it again. So this is the equivalent of the tire change in Formula One. It takes a little bit longer than a Formula One tire change does. But that's the kind of thing that we're going to do every single morning. If we can replace a couple of segments, then we will get through the whole lot in a year or a bit over a year's time. The secondary mirror is actually a 4-meter telescope. It's a convex telescope. It's the world's largest convex mirror made, because most of the other telescope mirrors we made are usually concave. This one needs to be convex, and it's hanging 65 meters up in the air. So keeping it there to the precision of a millimeter or so, which is what is needed to align the telescope and keep it aligned, is a really big engineering feat. Okay, nothing so special about M3. M4 I already talked about. So here are you can see the armies of actuators, 5,000 of them that will be behind the M4 mirror in order to provide the adaptive correction. You can see the M5 mirror, which needs to be extra lightweighted as well in order to provide fast tip and tilt. So that's made out of a material called silicon carbide to give it that special shape. Okay, and then here are the instruments on the Nasmyth platform that we are working hard at. So these are not ready yet. These are CAD interpretations or CAD models. There's Harmony with the yellow cylinder, which is a re-imaging part of Harmony. And the main cryostat is actually hidden under the structure here. There is an imager here called Mikado. That's the green. Sorry, Mikado is this dark green bit over here, and this is Metis, which is the mid-infrared instrument. So you can, here's a VLT telescope placed on the Nasmyth platform of the ELT. So that gives you a feeling, a feel for the size of how much bigger this new telescope is going to be relative to all the ones that came before it. I've nearly run out of time. I know. I'm just going to spend a few minutes telling you about what sort of science the ELT is going to do. So the ELT science case actually rests on 3 pillars. There is the science that we know that we are going to do. And then, of course, there is the synergy with other facilities such as the James Webb Space Telescope, ALMA, which works in the submillimeter, the square kilometer array working at radio wavelengths, etc. And then there is the discovery potential, right? So things that we don't know that we are going to look for as of today. So what the bit I can tell you about is the contemporary science cases, which themselves are broken into 3 groups, necessarily overlapping: planets and stars, stars and galaxies, galaxies and cosmology. So in the planets and stars section, what we are going to do with the ELT, of course, is look at planets around other stars, both in formation, so that's the circumstellar disk case, and in the planets themselves, so it's either direct detection or through radial velocity, or indirect techniques like transits, which are so popular these days in terms of finding and characterizing exoplanets. But because we are a much bigger telescope, we can see much fainter planetary emission, and we can also go much closer to the parent star to do direct imaging, because the diffraction limit of the ELT is only about 10 milliarc seconds in the near infrared. Then we can start to see individual stars in young star clusters and assess how they form. We can look for supermassive black holes in the centers of these star clusters, not unlike the one in the center of our own galaxy, for which was awarded the Nobel Prize just a couple of weeks ago. And then when we go on to other galaxies, we will, with the ELT, have the spatial resolution for the first time to see individual stars in other galaxies. So far, we can only resolve individual stars in our own galaxy. When we look at even the nearest galaxy, Andromeda, with the Hubble, we can just about start to resolve individual stars in the outskirts, but the inner regions are far too crowded. But with the ELT, going out to even distances like Centaurus A, which is the nearest elliptical or early type galaxy, and with a big dust lane in it, we will be able to see individual stars, take spectra of them, and thus characterize them and understand their evolution and their birth. All right, we will, of course, look at black holes in other galaxies, very distant ones, and understand how they came about and how the relationship between the mass of the black hole and the mass of the galaxy in which it sits has evolved over cosmic time. Going even further out into the far reaches of the universe, we will be able to see galaxies as they formed when they were only 1 billion years old, very, very young little children compared to the mature age of 13.8 billion that galaxies have today, or the universe has today rather. And we can see their velocity structure by looking at emission lines in gas, thus measure their masses, find out how massive they were, and look at how they evolved, how stars in them formed, the enrichment of what we call the intergalactic medium. And there are some exciting things like measuring the dynamical expansion of the universe directly over a 10-year time period. That's something for the 2nd generation of instruments for the ELT, really. But I think the big promise of the ELT is really going to be about discovery potential. Right, so just by combining this huge collecting area, which is what I talked about at the very beginning, and this huge increase in spatial resolving power, thanks to adaptive optics and thanks to the large size of the telescope, we are going to just open up new vistas where we don't know what we are going to be able to see, and we don't know what we're going to find. And that, I think, is what makes it all the more exciting to be part of this project, which is going to really revolutionize ground-based astronomy in the years to come. ELT is expected at the moment to see first light in November of 2025, and we expect the first instruments to operate a few months later. It's unfortunately probably going to suffer a little delay due to COVID-19. We don't know exactly how much yet, but hopefully not too much. So sometime in 2026, we hope we can be on sky and doing exciting science. So thank you very much for your attention. and for listening. I'll stop there and happy to take questions. I'll just run this movie while I should have turned the sound off. Sorry. That's just a promotional video from ESO, but people can type in questions perhaps while it's going.
Okay, thank you so much for that absolutely phenomenal talk. This is a mind-blowing initiative. This is humongous, not just in science, but also in effort and what it's going to achieve technologically and also ultimately in terms of the science. Thank you so much for this incredible presentation. So we've got lots and lots and lots of questions. I'm currently trying to sort through some of them. It's quite a lot of questions. One question that sort of jumps out, it's been asked quite a few times, is could you talk a little bit about the costs involved in building something like this? Sorry, I think you're muted. Okay, I think
Sorry.
yeah, no problem. Yeah, so a little bit about the costs involved.
Oh, yes, very good question. Yeah, so the whole telescope project has a cost of about 1.1 billion euros. And that's just the cost for constructing it. And of course, it will cost more to operate the observatory for its lifetime. So if you were to do a calculation of, what we call amortized cost of the telescope. So you sort of think about how much does it really cost to operate the telescope. For the current generation, the VLT, that cost works out to about €1 per second. And for the ELT, it will be 10 times larger. So it will be €10 a second. So if you think about, that telescope where you go to the top of a hill and you put in your 50p coin and you get 2 minutes worth of viewing time, for professional astronomers, you'd have to go there with your credit card and it would cost you €10 per second on the ELT. So the Harmony instrument project itself has a hardware cost that's for the adaptive optics and the spectrometer put together of the order of about 30 million euros.
Wow, big cost. Incredible. Okay, so we have one question, which is how much information is lost through the deformable mirror? Because the filtering, it manages to remove atmospheric effects, but does it also then remove weaker signals that would want to be retained?
A little bit. So you can think about it in terms of what we call the point spread function. So the point spread function is the response of the telescope to a point source that is infinitely far away. So a perfect infinitely sized telescope would just give you a pinprick on your detector. Obviously, because of diffraction limit, which I tried to explain, a real telescope would show you that airy pattern, which is, in the case of the ELT, quite tiny. It's only about 10 milliarc seconds in diameter. With adaptive optics, if the correction is partial, then you will get something where only part of the light is sitting in that diffraction limited core, and the rest of it is spread out over a much, much larger area, which is roughly the size of the seeing disk. We quantify the performance of the adaptive optics in something called Strail ratio, which tells us how close in peak intensity we are coming to that ideal of a perfect telescope that's diffraction limited. So 100% Strail would essentially be if you had a perfect diffraction limited telescope like you'd get in an idealized situation. What we hope to achieve with the ELT with real stars, bright stars, is something like 70% Strail. So that's pretty good correction for the adaptive optics. And the full width of the point spread function of the response of the telescope is very, very is indistinguishable from the perfect one. So actually, it's just mostly the energy that is lost in the core rather than the shape of the core. With laser stars, it's a little bit worse because we have to do this fancy tomography in order to reconstruct the atmospheric turbulence with our 6 laser stars, and that means that we get to only about 50% trail typically. So about half of the correction that you would get or the corrected image is half as good as you would get in an idealized situation. But that's in peak flux, or roughly also in energy. In terms of the diffraction limit, the resolution attained, that is very, very close to the ideal. So that's not really impacted by the imperfect correction by the adaptive optics.
Okay, thank you. So there are two questions which are quite sort of related, so I'll kind of put them together. So there's one which is, so to what degree could you use Earth-based and space-based telescopes to work together to complement each other? And I guess the second part from that is, how many of the sort of high resolution technologies that have been developed for the ELT could you potentially adapt or replicate even for space-based telescopes?
So yeah, well, space-based telescopes are expensive, about factor of 10 more expensive than the ones we can build on the ground. So for the same aperture, right? So to give you a rough idea, I think the VLTs, which are 8 meters across, that we have built, cost about 100 million euros each. For one 8-meter class telescope. By contrast, the James Webb telescope, which is being flown into space sometime next year, has about a 6.5 meter primary mirror aperture, so similar in size, and that costs about $12 billion now, something like that. Anyway, so yes, it is the cost of going to space is orders of magnitude larger than it is for the ground, from the ground. So the main motivation to go into space is to go to wavelengths where the Earth's atmosphere is simply not transparent. So there is nothing you can do from the ground, right? Because nothing gets through the atmosphere. So X-ray telescopes is one area, or far ultraviolet, where you can't, there's no hope of doing anything from the ground. The infrared is, or parts of the infrared is another regime. So being out in space, they don't really need, they don't have gravity, so they don't need a lot of the correcting mechanisms that we put behind our mirrors in order to keep their shape, because most of that comes about from the self-gravity of the telescope. They don't have wind buffeting, so they don't have wind shake problems. Turbulence from the atmosphere is gone as well. So really the Earth-based or the ground-based technologies tend to be rather different from the ones for the space-based telescopes. Some form of slow adaptive optics is planned for the James Webb. We call it more active optics because it's a slow correction. So you can correct for aberrations that you find in your telescope optics after you have launched it to some extent by adding a deformable component and correcting for some of them, but obviously they don't evolve in time as quickly, so you can just dial in a correction and keep it there. So it's a completely different set of technologies for space telescopes.
Okay, that makes sense. Great, thank you. I think we've got time for one more question, if that's okay. So could you tell us a little bit more about the data processing that goes on? Because undoubtedly you're accruing an incredibly large amount of data, telescope instrumentation end. So how does that work exactly, and what is the main limitation? Is it software or is it hardware in terms of getting the data and then processing it?
So the data rate is not that large actually, because we tend to expose for long periods of time in order to collect a lot of photons. So the sky doesn't change that quickly, most of the time. And so for a spectrometer like Harmony, a typical exposure time would be 15 minutes or half an hour. So we don't, while we have big array detectors, we don't read them out very often. Now, there are other reasons to read them out more often, because they're not ideal detectors. They have something called detector noise, and we'd like to bring that down. So by reading many, many times the same number, we can beat down the read noise. So we do it, we do multiple readouts. But even then, I think ELT facility is expected to generate terabytes of data per night, which is well within the capabilities of what we can store easily and manipulate later. So the post-processing of the data, we do a lot of it because we have to correct for the partial correction made by the adaptive optics. You can think of deconvolution, you can think of other fancier analysis schemes where you operate on the images that you have produced to try and tease out the physical parameters of the galaxy or object that you're observing. But that can be done offline. So in some sense, you have all the time in the world to be able to do it. So people are constantly honing their analysis techniques and doing more to try and tease out a lot more out of the data. I think what will become important in the ELT era, so far it hasn't been, is to simulate a lot of the science observations that we're going to make so that we can make best use of the telescope time, because it's so expensive to use these big machines that you kind of want to not leave yourself guessing as to what you're going to see. So we spend a lot of time doing quantitative simulations of the sort of science we'd like to do. We kind of make mock images, we analyze them, see what physical parameters we can derive with what accuracy, and only then will we go to the telescope to make the real observation. Of course, there's always the unexpected. That's why part of the reason why we build the telescopes. But we will try, I think, a bit like the particle physicists to do a lot more simulation work for the ELT era.
Great. Getting lots and lots of comments, just thanking you so much for explaining the ELT so well. And yeah, a lot of our viewers, all of our viewers are very, very grateful for that presentation and for your time.
My pleasure. If there are more questions, I can hang around. I'm not in a particular rush. I don't know if you need to shut down, that's fine. But otherwise, we can take a few more.
Okay. So there's one question, which is what challenges from the square kilometer arrays building process can be learned to carry forward for this one? Next.
Sorry, from the what building process?
From the square kilometer array or previous.
Oh, so the SKA is being built now. It's at a very different wavelength. So it's a radio telescope. It works very differently. And so I think, yes, there is a lot of infrastructure that exists in the communications industry that can be borrowed for SKA. I think the same is not quite true for the ELT. So the manufacturers who are making the segments have had to literally create a new factory assembly line for casting the glass and polishing it in order to produce one segment every couple of days if we want to get through the 1,000 or so segments in a few years' time. So I think that production has already started. We're already making mirror segments and polishing them. So we've had to go out to industry and get them to completely manufacture new assembly lines and new methods to build the kind of technology that is needed for ELT. I think some of it will come in handy for other uses. So adaptive optics, for example, is being used for medicine to get sharp images of the retina of the eye. So ophthalmic AO is a big thing nowadays. So, the progress in astronomy has helped a lot on other fronts on adaptive optics. There is also talk of using adaptive optics for Earth observation, where things look down rather than look up through the atmosphere, and also for military purposes, for, of course, keeping the collimation of laser beams shot from one aircraft to another, etc. So there are often lots of spin-offs, but I think it does tend to be the case that we often push the state of the art in technology to build the one-offs that we need for our telescopes and our instruments.
And so one last question. So to observe a variable star, is it better to use multiple telescopes or to use one sequentially? And why?
Oh, well, you need to calibrate, right? If you're going to measure variability, you need other stars in your field of view to measure against so that you have a datum against which to calibrate the variability. So you need something with a large field of view, and typically the bigger the telescope, the smaller the field of view, because it gets hard to control the aberrations over a large field of view. So adaptive optics also, because the correction is only applicable to a one direction on the sky, while it works for that particular direction, doesn't work for other directions nearby. So again, having a wide field of view doesn't go hand in hand with the use of adaptive optics. Now, of course, for variable stars, you may not necessarily need adaptive optics, although it does depend on where those stars are. If they are in other galaxies and you want to separate them from the other stars in the galaxy, then you do need a high spatial resolution, then you would need adaptive optics. But the variable stars are very important because they form the rungs of what we call the cosmological distance ladder. So we use them to measure distances very accurately, because we know the equations that govern their variability, and thus we know their absolute luminosity. So they serve as standard candles. So observing variable stars is very important. Hubble spends a lot of its time doing that. But yeah, probably the ELT is not the most, is not the best machine because mostly of field of view limitations.
Professor Thatte, thank you so much. This has been a brilliant talk, and there's been lots of engagement with it as well. So on behalf of all of our viewers, I'd like to thank you so much for your time. I know you're very busy right now, so thank you for taking
No problem. You're very welcome. It was a pleasure.
You're taking on an incredible task and leading an amazing project. So I hope everything continues to go well despite the pandemic as well.
Yeah. Thanks for the good wishes.
All right. Thank you so much.
Okay.
Thank you.